Welcome back, guys, to Urban Odyssey. In this video, we're going to continue our 6G white paper breakdown. And this section is section 7, titled 6G Radio Reconfigurable Transceiver Front Ends. Stick around, guys. Alrighty, guys, I hope everybody is doing well. This is, thankfully, this is a much shorter section. It shouldn't take us too long to get through it all the way. This is section 7, 6G radio, reconfigurable transceiver front ends. And before we get started, a number of people had said that seeing the new words and terms for each section was very helpful. And so we're going to do that again. We're going to get started with some new terminology. So let's go ahead and do that really quick. Okay. Very first one is a reconfigurable transceiver, a front-end reconfigurable transceiver. This is the shape-shifting weapon hardware that can instantly change its frequency, focus, and function. It is not just a radio, it is a scanner and a directed energy emitter that adapts to the target in real time. It enables all spectrum utilization, ensuring there are no safe frequencies for the human subject to hide in. 2. All spectrum sensing, total reality capture, the ability of the network to simultaneously sense and communicate over the full spectrum. Which is 1 gigahertz to 10 terahertz. This creates all spectrum cartography, a euphemism for the total mapping of the physical and biological environment managed by AI to enforce self-regulating societies, which really means automated tyranny. Next, we have NEMS, or Nano-Electro-Mechanical Systems. These are the molecular prison, the evolution of MEMS, smart dust. These are switches and devices on the nanometer scale. Unlike MEMS, which are microscopic, NEMS operate at the molecular level, allowing for the integration of mechanical control directly into biological structures and the Internet of Nano Things. QCL quantum cascade layer, the terahertz beam, a semiconductor laser used to generate terahertz radiation. In the context of 6G, these are emitters used to bridge the terahertz gap, providing the power source for frequency weapons that interact with biological matter at the quantum and molecular level. Plasmonic reflect arrays, the smart mirror, an antenna array made of metamaterials, often graphene, that can steer, focus, and manipulate beams of energy not by moving parts, but by changing its electrical properties. It can reflect signals in non-specular, unnatural directions to hit targets around corners or inside structures. Origami antennas, self-folding geometry, antennas that physically change shape, fold, split, or combine to alter their frequency and directivity. This is programmable matter in action, allowing the infrastructure of the kill grid to physically restructure itself to maintain a lock on the target. And the final one is Graphene Fermi Energy Tuning, voltage-controlled biology. The white paper explicitly states that graphene antennas are tuned by using a small voltage to modify their Fermi energy. This confirms that graphene inside the body via pollution or injection can be tuned to different frequencies simply by applying an external electric field, turning the human host into a remotely tunable antenna. Okay, those are all of the new terms. And so now that we have the grammar, we will go ahead and get into the white paper. 6G radio reconfigurable transceiver front ends. The massive increase in the number of wirelessly interconnected devices combined with the ever-growing demand for higher wireless data rates is leading to an overcrowded electromagnetic EM spectrum. To overcome the spectrum scarcity problem and increase the capacity of wireless networks, communication at frequencies beyond RF, i.e. from the millimeter wave to terahertz band, is required. To meet the data rate reliability and scalability requirements from RF to terahertz, transformative solutions, and I underline this because this comes up a lot in this section. This is an example of the soft encoded language that I am talking about. What does transformative solutions mean? Well, that means radical change. That means that we need to change things fast, and they need to be big changes. And so they can't really, say that we need radical change because that sounds radical. But they can say transformative solutions. So that's one example. There's a lot more, and I'll try to point them out as we go along. Transformative solutions are needed, which include the design, implementation, and optimization of frequency agile, ultra broadband reconfigurable systems. A system of this kind is able to simultaneously sense and communicate over the full EM spectrum, which is 1 gigahertz to 10 terahertz. Now, I did put up here that 1 terahertz is the same as 1000 gigahertz. So 1 gigahertz to 10,000 gigahertz is the same as what is right here, and serves as a major contributor towards the infrastructure needed for the next generation of wireless communications. To realize this vision, pioneering contributions are required in terms of 1. New devices that surpass the limits of CMOS, and that stands for not bad. There we go. Yeah, CMOS, because I think I've said that a few times that I couldn't remember what it meant previously, but CMOS stands for complementary metal oxide semiconductors. So when it says, here we go, surpass the limits of CMOS technology, what it's saying is surpasses complementary metal oxide semiconductors. New devices that surpass the limits of CMOS technology by leveraging state-of-the-art in materials science and nanoscale physics. 2. Heterogeneous integration of such devices, which is compatible with the electrical, thermal, and EMI requirements for reconfigurability and manufacturing scalability. 3. Novel, all-spectrum dynamic sensing and communication algorithms which maximize the achievable network capacity. The primary goal for 6G radio is to establish dynamic all-spectrum sensing and communication from RF to terahertz bands, therefore transforming the way in which wireless devices sense, access, and share the EM spectrum. To achieve such a goal, key steps include 1. Intelligent all-spectrum sensing solutions, and that's another one, intelligent. I mean, that could mean so many different things. I kind of interpret that as they're being vague on purpose, but you're free to interpret that however you want. Intelligent all-spectrum sensing solutions. 2. Transceiver hardware design and implementation. And 3. Spectral and energy efficiency optimization, as well as resource management. It is worth noting that currently reported works are fulfilling part of this grand goal by achieving dynamic spectrum sensing, or multi-band communications over several frequency bands. It is our hope to motivate advanced solutions to realize all spectrum communications through this section. The first subsection, A, dynamic all-spectrum sensing and access. In recent times, a concentrated research effort at the physical and link layers has driven exciting progress at RF frequencies for individual cognitive radios. So, I'm not really sure what people would make of that, because it doesn't sound good when you first hear it. But we will hear them out and see if this is just normal or if there's anything crazy here. But individual cognitive, meaning in your mind, cognitive radios. For example, a recently awarded research project by the Research and Innovation Program in the United Kingdom named 6G Mitola Radio aims to establish self-regulating societies. And I prepared for you guys. So, let's see, one moment. Let me bring that up so you can see it. That is the registration, because there was a citation on the paper, and I had to find that in the Internet Archive. So, cognitive brain that has collective intelligence. Great. Okay. So it aims to establish self-regulating societies, so that will probably be great for wireless communications with fairness and high efficiency. There's more code words. Should have underlined that, but I'll go ahead and do that. Yeah, that's coded language, because what that really means, and you have to understand, fairness and high efficiency, that means for them, not us. So in this self-regulating society, for people who have money and went to Ivy League schools and are in the club that's made for you and me, they will have fairness and high efficiency, and they will do that through force, coercion, and by everybody inhaling MEMS and now NEMS. Okay, so understand that clearly. That's why I say that, in my opinion, this paper is definitely maliciously worded. Like, they're using coded language that means certain things for them, but it's coded to appear as if they're talking about all of us, and that's just not the case. This research will facilitate seamless convergence across heterogeneous wireless networks with intelligent decision. It means by them. They are the intelligent masters, the illuminated masters. And so that means intelligent decisions will be impacted or driven, affected by them, made by radios to maximize the quality of experience for end users. One step further, a major challenge is to develop innovative spectrum sensing and sensing-informed communication and network optimization techniques for dynamic access to all spectral resources. Within this context, the targeted breakthrough would be the development of wireless network-aware state inference using all-spectrum cartography for cognition over the swath of frequencies from RF to the terahertz band, along with cartography-constrained algorithms for the physical and cross-layer control protocols. Artificial intelligence and associated learning algorithms should be investigated for dynamic spectrum sharing with a minimum cost and interference. Probably this right here is what I just showed you. The that right there. That was the one that I had to get in the Internet Archive. Yeah, uh, interference, I think. The techniques developed should wholly exploit the capabilities of the hybrid front ends, which include a multi-band transceiver design and solutions for resource management. There we go. Subsection B, multi-band transceiver design. The optimal selection of materials and devices needed to enable all spectrum communications is vital to the success of any multi-band transceiver design. Existing solutions mostly rely on CMOS, complementary metal oxide semiconductors, CMOS, for multi-band operations. But such an approach only works well in narrow bands. Moreover, solutions based on software-defined radios, SDRs, have high energy consumption and carbon footprint, consuming several watts in operation. Now, this actually makes me kind of think about all the data centers, you know, how they consume like more water than people drink in a year. And that's actually 100% legit. I don't have the exact numbers in front of me, but I encourage literally everybody to just do a simple Google search for the energy and water requirements of data centers, and it will blow your mind. And maybe, just a maybe this is one of the things they've got going there. Software-defined radios have a high energy consumption carbon footprint, consuming several watts in operation. Instead, novel approaches based on metamaterials, remember meta means dead, NEMS switches, and even Nano-Electro-Mechanical Systems, NEMS switches should be sought to implement hybrid front ends, figure 8, which we're about to see, which are able to simultaneously sense the EM spectrum, identify the best available band, and communicate over it at frequencies anywhere from 1 GHz to 10 terahertz. Furthermore, fast-evolving deep learning algorithms serve as an efficient solution for identifying available spectrum tuning channels and adjusting RF power levels. To realize this vision, new techniques in materials and devices, integration and packaging, and spectrum sensing and communication are necessary. At the RF and microwave frequency bands, a combination of low-risk, mature CMOS technology with less mature, potentially transformative technologies, including quantum cascade layers, which was one of the words that I showed you at the beginning, and new plasmonic technologies based on graphene and other 2D materials, will be able to provide optimal tunabilities as well as a high quality factor, the Q factor. The heterogeneous integration of discrete devices into a fully functional front end will require innovation to satisfy material compatibility, EMI shielding, thermal dissipation, and scalability requirements. On the other hand, metamaterials and nanomaterials will be deployed at sub-terahertz and terahertz bands based on recent advances in nanotubes and graphene, as well as other single-atom thin semiconductors. Space-time frequency coding in metasurfaces will also allow programmable and fine-tunable radio access at millimeter waves. Optimal control of the front ends requires innovative all-spectrum sensing, utilization and sharing techniques, new waveform and hierarchical modulation designs to maximize the capacity and distance in ultra-broadband systems, and scalability networking solutions which are able to support the envisioned node density in future cyber physical systems. Cyber physical systems. The combination of several cutting-edge techniques can help maximize 1. Spectrum utilization towards all spectrum utilization, 2. Data rates towards terabit per second links, and 3. Network user capacity, billions of interconnected wireless devices. The proposed technology will enable a plethora of applications in the consumer, military, industrial, and medical fields, including transformative networking architectures designed to meet the scalability demands in future cyber physical systems. Guys, I'm telling you, this paper is got such high level language in it. This is I'm trying to read this as slow and as clearly as possible so that you guys can reference back to it. But sometimes it's a tongue twister. So real quick, now that I've finished this section, let me go ahead and show you figure 8. Here's figure 8. Conceptual design of a hybrid front end for dynamic all spectrum sensing and communication in 6G. Okay, subsection C, reconfigurable front-end scheme. Accompanying the dynamic all-spectrum sensing and multi-band operation, agile front ends should also be equipped with reconfigurability. In terms of hardware design, the plasmonic reflect arrays can be deployed in the 3D environment with a size ranging from 1 millimeter squared to 100 millimeters squared. That is hard to wrap your head around, depending on the operating frequencies. You guys should understand the things that are being talked about in this paper are basically programmable matter. They can control waves, they can control particles, they can steer the beams, and they want it inside of not just you, but everything. All the birds, all the plants, all the trees, all the dirt, all the water. They want it in everything. Owing to the sub-wavelength size of their elements, the plasmonic reflect arrays are able to reflect signals in non-conventional ways, which include controlled reflections in non-specular directions, as well as reflections with polarization conversion. In order to adapt to dynamic frequency operation, achieve various levels of directivity, and allocate multiple beams, the aperture of plasmonic reflect array antenna can be controlled mechanically through folding, splitting, or combining in a 3D space. Existing prior art using origami antennas works well in systems using a single metal antenna as reported in those subsection citations. However, to achieve reconfigurable continuous aperture antenna arrays, plasmonic reflect arrays offer a high degree of freedom with the compactness of unit element distribution. On the other hand, electronically controlled reconfigurable antenna arrays are envisioned by leveraging the tunability of plasmonic antennas. In particular, one of the relevant properties of graphene-based plasmonic nano antennas is the possibility to change their resonant frequency by utilizing a small voltage to modify their Fermi energy. The possibilities to tune an antenna or group of antennas at different frequencies without any mechanical modification, as opposed to other multi-band antenna arrays that utilize MEMS or NEMS to create origami type structures, enables beam forming not only across space but also across frequencies. D. Open problems. The biggest hurdle to be overcome lies in the implementation of an integrated ultra-broadband hybrid front end that is capable of sensing and communication from the RF to the terahertz bands over a target distance of a few hundred meters. Meeting this multidisciplinary challenge requires us to 1. Close the terahertz gap by developing new device technologies. 2. Design and integrate reprogrammable circuitry, interconnects and antennas that can support all spectrum operation. 3. Develop new material integration and packaging techniques to satisfy the electrical, thermal, and EMI requirements of disparate bands. And 4. Develop scalable all-spectrum communication using the front ends. So, for instance, like just this final little part of this section 7, they tell you what these quote unquote challenges are, but at the same time they're able. I mean, they're well aware of what research is going on. You know, maybe some of it they can't talk about, but to a degree they're using so many simple words in such a advanced sentence, if that makes sense. For instance, let's see. Develop new material integration and packaging techniques to satisfy the electrical, thermal, and EMI requirements. So, new material integration and packaging techniques. You know, that's pretty broad, but what do they mean by that? They don't really give you any more information. Develop scalable all spectrum communications. Uh, I mean, that's just a very open-ended challenge, I guess. And I do think that they've solved a number of these since 2020, especially when you start looking into some of the like the citations and whatnot. I'm not going to cover those in my videos on the paper. I'm going to let you guys go through those on your own, or you can actually just take the paper, you can upload it to like Chat GPT or something, and you can have it tell you and explain to you what some of those citations are about. In certain cases here, you have a lot of learning to do because some of these topics are mind bending at the very least. You know, it actually requires you to change the way you think because never before did people ever, and still to this second right now, people who haven't seen any of my videos or videos on the topic or information on the topic, or they haven't read the 6G white paper like we're doing right now, they wouldn't have any idea that any of this is happening, possible, or even in the realm of possibilities. They had no idea that people can use millimeter waves. They don't have any idea that there's nano-electromagnetic mechanical system. They have no idea about any of this, and that's why even if I don't understand all of this fully, I'm trying to give it to people so that they can know it exists and be prompted to learn more about the topics. And that is also why I've got a lot of words going into the new directory here. This is available on Substack, the official urban.substack.com. At the top, you'll see a little option on the menu that says tables. You click that, and it will bring you to this. And right now we have, I don't know, maybe 120 different words in here. So as, for instance, the definitions that I showed you at the beginning, those got put into this table before I made this video. And so that's part of the research that I'm doing parallel to making these videos. And so you can search on here, and I highly encourage people to do so because this will help you kind of remind yourself what these words mean. So let's see. NEMS right there, and there's a little image. If you click on the little image there, it'll give you the images like I showed you at the very beginning of the video. And so I'm trying to keep this as up to date as possible. And if anybody sees something that's not on there, or they would like to contribute to it, you're more than welcome to. I will actually update the tables page, and I will provide like a link or a form or a survey or something for people to do that. But that wraps it up for section 7, and so I will see you in the next video. Take care, guys.